Good morning. My name is Mariusz Dąbrowski. I am the president of the Jerzy Stelmach Eureka Foundation, which deals with interactive education and popularization of the frontal scientific research. The foundation gathers active scientists, and therefore, for a couple of days, we offer you lectures and debates under the project Science and Technology Progress Closer to the Society. Session code is N2, entitled Dark Universe, Problems of Contemporary Cosmology. The project is co-financed by the Polish Ministry of Science and Higher Education under the Social Responsibility for Science 2 program, and its aim is to bring the achievements of outstanding scientists to the general public. Our session will be held in English and in Polish. There will be 4 lectures and 1 discussion session today, on Monday, the 10th, and on Tuesday, the 11th. English part, 3 lectures and 1 discussion session will be translated into Polish and placed on YouTube in a couple of days after the session. There are some technicalities which we cannot avoid to make it parallel. The main lecturers of our session and also the discussion will be Professor Vincenzo Salzano, Professor Salvatore Capozziello, and 2 special lectures by Professor Leandros Perivolaropoulos and myself on Monday. I am pleased to announce that today's lecture will be given by our guest, Professor Vincenzo Salzano, who will give us a talk entitled Dark Matter, What is it? Good morning, Professor.
Good morning.
Before I start the lecture, before I will let the scene to our lecturer, let me say a few words about the scientific career of our guest. Professor Vincenzo Salzano is now a professor with the Szczecin Cosmology Group at the University of Szczecin. He accomplished his MSc studies at the Faculty of Physics, University of Salerno in 2005, and then started the PhD studies at the University of Napoli, Federico II, finally ended with the PhD entitled Constraining Extended Theories of Gravity by Large-Scale Structure and Cosmography. This was 2008. Later, he had 2 postdoctoral visits. One was at the Institute of Theoretical Astrophysics, University of Oslo, years 2009-10, and then he took another postdoc position at Basque University in Spain from 2010 till 2014. And in 2014, he joined the Szczecin Cosmology Group to work with the grant. I had the pleasure to actually be the main investigator of this grant related to the issue of the variability of the fundamental constants in physics and cosmology, and now Professor Salzano, then as a postdoc, was appointed into this grant. He started loving Poland, and after being appointed for this grant, he presented his habilitation degree in Poland in 2018. and now, as I said, is a professor in our university. Professor Vincenzo Salzano last 2 years was enumerated, was listed, mentioned as the top 2 scientists in the world, years 2023 and 2024. His publications reached the number of almost 4,000 citations with the H index 24. And he also, which is non-trivial, also co-authored with 2 papers with the Nobel Prize winner, Professor Adam Rees. Currently, Professor Salzano is running a very interesting grant at the University of Szczecin entitled "Can a Slime Mold Help Us Alleviate Cosmological Tensions?" However, today, Professor, as I said, will say us more on the issue of dark matter, which is one of the main problems in cosmology, according to our main title of the session. Professor Salzano, now the scene is yours. Please start your lecture and tell us what is the dark matter.
Thank you for the very kind introduction. I will share now the screen. I guess that now you can see it, right?
Yes, we can see it. Perfect.
Perfect. So I will put it like this. Okay. So thank you again. And I decided to change a bit the title, just dark matter, because actually I have to tell you first some things about how do we know that we need dark matter. Then I will tell you about all the observational probes which we have collected so far. And finally, I will try to tell you what do we think is dark matter. And I want to avoid any spoilers, so we can start. So the first thing is, how do we know that we are missing something? I use the term missing because dark matter, it will become clear later, but it's dark because actually it's sort of invisible. We cannot see it directly, more or less, because does not interact with light. You can see me because the electrons, the protons, the neutrons, which we are made of, actually scatter light. So light hits me and then arrives to you. Dark matter is dark because that's nothing like this. So the first question will be, so how do we know that there is dark matter? And the answer is gravity. But I need first to make a short historical review about gravity because most of you, I guess, are used to think about gravity remembering what you did in the high school. This guy is Isaac Newton at the end of the 17th century. You know the history. He was sitting in the countryside of England. He was below an apple tree. Then an apple fell, and he got the genius idea of how to describe gravity, the attraction or between two masses, two bodies. And this is the usual formula which you studied at high school. It tells you that the gravitational force is proportional to the masses of these bodies. It's inversely proportional to the distance, so the farther they are, the less is this interaction. But I have to tell you that although this theory works perfectly well around us, and even out of the Earth, if we want to describe let's say generally the interaction between sun and the earth, the earth and the moon, it started to have some problems. It means that it was not able to describe everything which we were observing. We have to wait 200 and a bit less than 250 years before this guy, who for sure you know, Albert Einstein, he revolutionized the idea we have about gravity with his theory, general relativity. And he gave a sort of new theory, but of course, this new theory was just more general than Newton. It was not canceling totally Newton, because that we know that Newton theory works in some range. But he extended this theory. And I have to say, he also made it more complicated for us physicists, because instead of having one single equation, these are called Einstein equations. So because they are more than one, and they are also complicated mathematical objects because they are differential equations. And I hope that none of you has ever to do with differential equation, because differential equations are one of the worst beasts to tame in physics and mathematics. But even so, his idea of how gravity should work, what is the nature of gravity, was mind-blowing, because here I wanted to report a sentence from a very famous cosmologist, Wheeler, and he, let's say, summarized the nature of general relativity in this way. Matter tells space how to curve, and curved space tells matter how to move. So I have this video can be found in YouTube. I have downloaded it so that you can see how we can, no, sorry, not here. I have it saved here. So now the point is, imagine empty space. So there are no masses. We can imagine this space as a flat, elastic plane. I have to warn you that many theoretical physicists, even some colleagues from our group, don't really like this example, because they say that it's too easy, simplifies too much. I agree, but I also think that if you want to convey the idea of how gravity works, this is one of the best examples which we can have. So what is the point here? In an empty space where there are no masses, the space can be considered flat. But now what happens when we put a mass? Oh, I'm sorry, because YouTube, I was opening YouTube because I wanted to avoid ads. But so what do you see here? There is a mass. It can be the Earth, the Sun. And what it's doing is bending the space. It's carving the space. So you can imagine, if now I put a ball here, what is going to happen? This ball is going to fall. So imagine you are inside on this central. What you will see? You will see this ball falling to you like it is attracted by you. And on the other hand, if you are on this ball, which is left to falling, what you see that is that you are falling on this body. That's, in few words, is gravity. So is, as you can see here, he launched a ball with some velocity, and what this ball is doing is to orbit around this mass. Of course, if the velocity is small, it will spiral down inside this mass very fast. Otherwise, it will start to orbit it. And this is, said very easily, what gravity is in general relativity. So whenever we have a mass in the space, this is bending the space-time, and let me say in this way, falling into this wheel is what we call gravity. Now you can see here, if we have the sun, which is huge compared to Earth, this well, gravitational well, is bigger, deeper than the other. Even we ourselves are creating very small gravitational wells inside the gravitational well of the Earth. But we are not attracting our friends because this attraction is very, very small. But now I have to tell you something, because actually, you see here there is a grid. You know that we need grids, coordinates, when we want to locate and define the position of things in the space. But what is crucial in general relativity is that it arrived after another theory from Einstein's special relativity, in which he unified time and space. He started to say time is not absolute, is just another coordinate. So here you have to imagine this grid is not only indicating a grid in space, but also grid in time. And as you can see, when you go closer inside this gravitational well, this grid is distorted. And this distortion actually is general relativity makes a lot of crazy, apparently crazy predictions like time dilation. What does it mean, time dilation? As you can see here, this grid is distorted. So what is happening in general relativity is that time inside the gravitational well is going differently than time outside. And you might think that this is just a crazy, how it's possible that time is going differently if you are inside or closer or farther than a body. Well, these crazy predictions are very useful for movies. I know that most of you have watched Interstellar, and this picture is from this planet which is orbiting Gargantua, this very massive black hole, where there are these tides which are huge. And if you remember, when they have to decide if to land on this planet, which is, remind, is orbiting around a black hole, and the black hole, what they do is to create this gravitational well is extreme. So there is a lot of distortion. And if you look, this is taken from YouTube, so there is no violation of copyrights. You can find this image where the people are discussing, okay, we can go down, I can bring you, the character is saying, I can bring you with the spaceship. But then this guy who is a physicist say, guys, wait a moment, because if we go there, being closer to the black hole, time is going differently. And actually, he calculates that 1 hour on that planet is 7 years on the Earth. And the people look at him like, are you crazy? And he ends with this sentence, that's relativity, folks, that's true. General relativity predicts time dilation, and time dilation is true. Because, for example, it also has technological impacts. GPS, you all know what is GPS. We have our mobile phones. If we put in Google Maps the position of a place where you want to go, Google Maps is going to tell you where it is, how to arrive. But how does this work? Well, this works with GPS. Said very easily, what happens is that your mobile is sending a signal to the satellites. Then these signals go back, and whatever the smartphone does basically is to calculate how far is the satellite or your position from the satellite, basically multiplying the speed of light, because the signal comes out at the speed of light, times the time to go back and forth. It sends this signal not to one satellite, but three at least. That's why it's called triangulation. But I have to tell you something. Remember, here we are on the Earth, but satellites are orbiting around the Earth. So you have to imagine that we are inside the gravitational well, and the satellites are outside. So we are in different positions respect to the center of this well, and time goes differently. So if your mobile phone does not take into account the general relativity, then when you put the address of some place, for example, I don't know, something in Szczecin, Galleria Cascada in Szczecin, instead of arriving to Galleria Cascada, you will arrive, I don't know where, in Poznan. So this is just to tell you that if you don't take into account the difference in time between us and the satellites, GPS is useless. But GPS works. Why? Because the calculations which are required from general relativity and also from special relativity are inside the software which calculates this. So that's why it works. GPS works because we take into account the fact that here and on the satellites, time flows differently. But then these crazy predictions from GR are useful also for us to do science. And for example, I can tell you that the universe is continuously playing hide and seek. What does it mean? It means that we can see things which are actually hiding. Let us suppose here we are on the Earth, this is the sun, and here there is a star. So let us suppose that we are looking at this star during the night. So the sun is not here. If the sun is not here, the space between the star and us is flat. So basically, the light ray will move straight to us, and we see the star in a certain position. Now, what happens during the day? We cannot see the star, first because there is the sun, which is illuminating everything. But even if we were able to see it, to look at it, the star will be covered by the sun. Instead, in general relativity, there is a prediction and says the following. The light ray, for example, let us follow this one, which goes here, technically should continue straight and not reach us. But when it arrives here and feels the curvature produced by the sun, what it does is to be distorted. So there is a curvature here. So this light ray, which in principle should not arrive to us, actually arrived to us. And where we see the star, where we know that we are going to see an image, a fake image, not where it is real located, but here. This is nothing different from if I'm hiding something behind my back and you are in front of me, you cannot see. But if I put a mirror on the side, you can see the image reflected. So you know that this image is not the real, it's a fake image. This is called gravitational lensing. And for example, I can tell you that if you stick to Newton gravity, you cannot predict. Actually, in principle, you could, if you suppose that a light is made of particles with a mass. But at the time of Newton, we didn't have this idea. Light was just a wave energy, so it was not described as mass sequence of mass particles. But some scientists said, okay, if light is a sequence of masses, in principle, it should feel gravity. So there should be this distortion. But the point is that if you calculate this distortion, so basically this angle between the real image and the fake image in Newton and in GR, the estimation from Newton is wrong. The estimation from GR is correct. And actually, after only 3 years that Einstein proposed his general relativity, there was a sun eclipse. So this was very interesting because, in principle, you can measure during the night the position of a star, and then during the sun eclipse, so during daylight, because the sun is covered, the sky is dark. So in principle, you can see stars. So what they did was to measure some stars, their position during the night and during the day when there was this sun eclipse. What they found, let us look what is inside these points. Double images. So what you are seeing here is, this one is the position of the star during the day, the night, and this one is the position of the star during the day, when there is the sun who is distorted. So you can see that there is an angle. You calculate this angle, and you can see that all stars have this double image. You can calculate this angle, and you see that it does not agree with Newton. It agrees with general relativity. So this was one of the first confirmation that general relativity was correct. And if you are thinking that this is something not very common in the universe, I have to tell you that actually it happens thousands of times. In every image we take, there are thousands of events of gravitational lensing. This type of lensing, because of, I will tell you other things later, is called strong lensing. And here I downloaded, this is a simulation. So in this simulation, you have to imagine that you are on the Earth. Then you see here, this mass is going to pass between you and these galaxies. These are not stars, these are galaxies. And I can show you that when this mass is passing between us and the galaxies, can you see it? It seems that the galaxies are moving, but they are not moving. They are going to be distorted by this mass. And you will see what happens when it arrives where there are more galaxies. Can you see it? these are they are distorted. And when there is almost a perfect alignment between us, you see, this galaxy, instead of looking like a bulb of light, looks like a ring. And this happens, and you can see that all other galaxies are distorted. They become arcs. And again, you could think that, okay, but do we see this? Well, yes. I can show you some images. So here, let us look here, this is a cluster of galaxies. So some galaxies are closer together, so they are moving together. And let us see what happens here. Let us zoom here. Do you see all these arcs? These are not galaxies. These are images of galaxies which are behind these bright objects, which are distorted. And if you go here closer, you can see even larger arcs. So all this is strong lensing, and inside each image, there are thousands of these events. They also create some very nice picture, like this one, which was called by NASA a smiley face. These two objects are on the foreground, and in the background, there is a galaxy which we cannot see. In principle, we could not see, but these arcs are actually objects which are behind, and they create this sort of pumpkin smile. And you have a lot of these rings. This is just a small collection of all these. They are called Einstein rings, after Einstein, of course. And for example, here you have this image. You would think that, okay, these are not stars. We're talking about galaxies here. They are very far objects. How do we know that these are not four objects which stay there just by coincidence? Well, because what is happening here is that between us and this quasar, it's a kind of galaxy, there is a galaxy which is distorting light. So these four images, these four objects which you see, are not four different objects, but they are four different images of the same object. And someone could say, but how do we know that they are four different objects? Well, because we collect light from them, then we can analyze it. This is called spectrum of the galaxy. And you have to think that this spectrum is a little bit like fingerprints. You know, there is this, I don't know if it is totally true, but there is this legend that there is no one on the earth which has your same fingerprints. Just to say that fingerprints are characterizing one single person on Earth. Spectrum is the same. You cannot find totally equivalent spectra. They can be very similar, but not totally equivalent. And if you compare these four spectra taken from these four objects, you can see that they are basically equivalent. They have the same spikes exactly in the same place. They have the same behavior. So that's how we know that these four images are the same object, which is behind. One last, I want to talk about it because it allows me to tell you how we use gravitational lensing also to find dark matter. Because gravitational lensing produces another phenomenon called time delay. Because, for example, this light ray, compared to this light ray, as you can see, has to run shorter path. So if you have a source here, which is varying luminosity with time, basically on the Earth, you will see one image changing luminosity before the other, because the other had no time to arrive. It will arrive with some delay. Not only, but this light ray passes closer to the galaxy, so it's more inside the gravitational well. So there is also this time dilation produced by general relativity. And let us give a look at this. This, again, is a cluster of galaxies, but the name which has been given, Refsdal, has been given actually to a type of object which is called supernova. Supernova is an object which, I don't want to enter into the details, but it's an object which experiences a sudden increase of luminosity and then fades out forever. So we are going to zoom here in the center. And what we see is this. This galaxy is a galaxy which is behind these more luminous galaxies. So it's an image, a fake image of a galaxy which we could not see. But what is peculiar here is that there are these 4 points. And from the spectrum of these 4 points, we know that it is a supernova. So this galaxy, which was behind, had an event called supernova, which produces bilensing of this foreground galaxy, 4 images. Now, what we do as a scientist, we start to model the mass of the lens. So what we do basically is we start to propose models for how the mass of this lens is distributed. And we do what is called best fitting. So we try a model. It is able to reproduce this gravitational lensing event? No, so it's the wrong model. And we proceed until we find a model, so a mass model of the lens, which exactly produces this image. And these scientists found something interesting. They put their model, they found the best fitting model, which was able to produce this image, but also they calculated that there should have been another image of the same supernova appearing with some time delay. They calculated that it should have been more or less closer to the center of this group of galaxies, and more or less the time delay should be around 1 year. Guess what? The first 4 images were observed between fall 2014 and spring 2015. And then in spring 2016, they found another image appearing more or less where they were waiting. And this image has a spectrum equivalent to the other 4. So we are seeing another image of the same supernova. So the message which you have to take into account here is how we use gravitational lensing. We model the mass distribution of the lens. So we calculate how much mass should be in the lens in order to describe lensing. Now, here it comes, dark matter. Sorry for this large introduction, but I needed to give you the input to understand how we see that. We don't see. How we know that there is something which we can describe with dark matter. So this image is a cluster. It's called the bullet cluster. Bullet in English is when you shot, there is the projectile which comes out and actually can kill you. This is the bullet. And in this image, which is the image which you will see in the visible band, so using light, which our eyes are sensitive, show you to follow my, here, there is a group of galaxies, and here there is another group of galaxies. Now, in this image, there are thousands of galaxies, but these two groups of galaxies have a peculiarity. We can measure where they are, the distance. And we know that these two are more or less at the same distance. So it's like to imagine that we are creating a sheet in the sky, and on one sheet, you have these two groups of galaxies. All the others are on the foreground or in the background. Okay, beautiful image. But now let us look how the same image looks when we look to the X-ray band. X-ray is, you cannot have a lot of X-rays because it's very high energy particles which could damage your cells. And here we are looking at X-ray. What does it mean? We are looking at gas which is so hot that emits light in the X-ray band. So we can only see it not through our eyes, but through very specific eyes. Here you can see the name of the satellite, Chandra. It's an X-ray telescope. So it can look to things which emit light in the X-ray band. And here, this is very peculiar. Later, in few minutes, in few slides, I will show you this image overlapped on this one. But for now, I can tell you this is gas. You can see, or listen to me, but more or less you can see that there is one bulge of gas here. Then it seems here there seems to be a small separation, and then there is this other bulge of gas, which is also very peculiar because you can see it's like something entering, like an arrow, no? I don't know if you have the same, you are thinking the same, but this looks a lot similar to this other image. So you have a bullet, that's why it's called bullet cluster. It's not actually one cluster, but it's two clusters. And the cluster which now we see on the right is the bullet. And this here, which you see, could be thought like these pieces taken from the apple. It's not exactly this, but I will explain you now. So what we are seeing here, the bullet cluster actually is not one cluster. Cluster means group of galaxies. There are two clusters. One big, which now we see here on the left, and one smaller, which we see now on the right. These two clusters, billions of years ago, were on the opposite side. So the small was here and was moving through the biggest one. Actually, galaxies move, even if they seem not to be moving, but they are moving. The fact that we don't see them moving is because they are so far from us that we cannot perceive their motion in the lifetime of human life. So what we have been reconstructing then after is that this small cluster was before here and there was some relative motion, was passing through the biggest one, and now we see it here. Now, why we see this sort of bullet shape only for gas and not for galaxies? Well, because you have to imagine that the space between galaxies is huge. So even if you have two clusters which collide, basically galaxies can pass through each other without collision, at least within a certain time interval, which is huge. But gas is everywhere. When these two clusters are colliding, the gas of one cluster interacts with the gas of the other cluster. And because here we have less gas, because there is less, the cluster is smaller, feels is more disturbed than the other one. But basically here we are seeing a shift. So due to this collision, the small cluster is like arrow shaped, and the gas of the biggest one has been shifted a bit respect to galaxies. So now it arrives. We are going to enter now this sort of police book. How do we interpret all this data? So what the galaxies are telling us? Well, here we arrive to another type of lensing. So the lensing which I told you before, which produces these arcs and these images, is called strong lensing, because you have these large objects which perturb and so on. Here we have something which is called weak. It's much more subtle, but it's very interesting. So imagine that there is no bullet cluster. So in this image, there are a lot of galaxies on the background. What is their shape? Well, in principle, we know that there are elliptical galaxies they are flattened in different ways. There are spiral galaxies which are oriented in different ways. So in general, if you take a certain region of space and you calculate what is the average distribution of these shapes, you will find that they are random. So you can find 10 galaxies which are circular, 10 galaxies which are very flattened, 10 galaxies which are half flattened. You can find any kind of distribution in terms of shape. But what happens when you put masses? So for example, if I put a mass now here between us and these background galaxies, what happens to the shape? Well, if it is strong lensing, they could be deformed, like arcs. So you see them clearly. But in weak lensing, what you can have is that the shape of these galaxies is only weakly disturbed. So for example, a galaxy which looked like circular before, spherical, now you see it a bit elliptical. If a spiral galaxy had the arms oriented horizontally, in principle, due to weak lensing, you can see a distortion, so that instead of being horizontal, looks a bit inclined. And this is what is happening with the bullet cluster. Here we have the bullet cluster. Here we have all these galaxies with random oriented shapes. But the image which we have is that the light from these galaxies is distorted by the mass, the total mass of this bullet cluster. And as you can see, around a mass, the orientation of the shapes is not random. Somehow has imprinted in it the distribution of mass. So what we have here, what are these green lines overlapped on the galaxies? This is our reconstruction of the mass of the bullet cluster. What we have done is to start to put different mass models until we were not able to describe perfectly the lensing events which were there. So what is here? It means that here is more dense, so the gravitational well is deeper, and the more you go to the outer parts, you move to the parts where the gravitational bending of space-time is less. And what you see here is that the peaks in densities are centered on the galaxies. Now, let us see what happens when we have gas. When we have gas, we see a shift. I already told you that in principle, this shift is normal because gas is stripped, feels more this collision than galaxies. But there is a problem. Actually, there are two problems here. First, we know that there is here in blue, I'm putting what was before like green lines. So this tell you where the total mass should be distributed. And what is the problem here? This is our reconstruction. So for us, in order to describe the weak lensing, assuming GR as a theory of gravity, the mass of this bullet cluster should be distributed like this. So centered on the galaxies. But there is a problem. The problem is the following. We know that there is about 3 times more gas than galaxies in the bullet cluster. So if you remember, this bending of space-time is proportional to the mass. So in principle, there should be more lensing where there is the gas than the galaxies. And here we are finding the opposite. We can describe lensing if we have mass distributed more around galaxies than gas. And now we arrive to the other shocking part, that in order to describe lensing, we need at least 70% of the total mass to be invisible. It means that if we want to describe this weak lensing, 70% of the mass of the bullet cluster is not galaxies, which we can see, is not hot gas, which we can see in the X-ray, but it's some mass which is invisible. What we are seeing here, dark matter. This is dark matter in action. We are seeing how dark matter is perturbing the collision and the dynamics of these two clusters. And this bullet cluster, the paper describing this event, was in 2004. Here I wanted to put also for curiosity the title which was given, because titles are one of the most important parts in articles. I generally leave this duty to my colleagues because I'm very bad in writing titles. But here you have all the information which I told you, said in technical terms. So you can see weak lensing, mass reconstruction, because we reconstruct mass using weak lensing. Of the interacting cluster, 1A is the name, the catalog name which has been given to the bullet cluster. And notice what is after. Direct evidence for the existence of dark matter. This is 2004. Some colleagues might not be totally agree. It was a sensational title. But I have to tell you the history of dark matter is actually older. Not only older, but if you are thinking, okay, but you have observed one single cluster, maybe it's the only case. No, dark matter is everywhere. So you have to know that the first time we had dark matter notion was in 1933. So almost 100 years ago. This guy was an astronomer, Swiss astronomer, Fritz Zwicky. And in this image, he looks like when you were children, when you were a child and you were doing something bad, and your mom was looking at you like saying, you have done something really bad. And this picture is very nice because it shows you that very important and famous astronomers, physicists can be funny, as the image of Albert Einstein, which I showed you before. But also it's funny, the coincidence with this dark matter. Because what Zwicky was doing is to measure velocity of galaxies in clusters. So this image here There are thousands of galaxies here, but we have to focus on these brightest ones. They constitute what is called the coma cluster. He was measuring the velocities. How we measure velocities? Well, this is, I guess, that you, if I give you the right elements, you can get it. So we know very well when we have light and we let it pass through a prisma, it is decomposed, and you have the composition of the light in all these colors. This is called continuous spectrum. Then what happens if we have a star or a galaxy, and between us and this star, there is cold gas? You get this. So as you can see, this is like the continuous spectrum, but there are some lines which are dark, because it means that light in this region was absorbed by the cold gas. That's why it's called absorption spectrum. If instead we have hot gas and nothing between us and this hot gas, you will see a complementary vision. So you see everything dark, but only some lines are brighter because these are emitted by the gas. And this is called emission spectrum. What is the nature of this? Well, the nature is that each element creates its own light. This is something which you know very well when you look at fireworks. The fireworks have different colors because you are burning different elements. You are burning chloride, you are burning sodium, you are burning barium. And each of them, when you make it very hot, like in the fireworks, when they explode because they are hot, they emit light. So they have this emission spectrum. And on the other hand, why there are these absorption spectrum? Because if, for example, as you can see here, there is hydrogen in the cold gas, the hydrogen will interact and absorb only the lines which correspond to this. And we know this very well. Otherwise, we would not have fireworks. So what we do is in the laboratory, another thing I was forgetting. Then there is another point, Doppler effect. Everybody knows what is a Doppler effect. When there is an ambulance and you sit just close to the ambulance which doesn't move, you hear the sound of the siren. But what happens if the ambulance is approaching you? You hear a high pitch. And this high pitch is because sound is a wave. And when it is approaching you, the ambulance is approaching you, you are squeezing this wave. And squeezing this wave corresponds to high pitches. If you are playing piano or guitar, you know that the length of the chords produce different pitches. And the shorter are the chords, the higher is the pitch. And here you have the same. When it is going far from you, what is happening? You hear the sound becoming slower and slower and lower and lower. And that's because sound, which is a wave, is stretched out. And this corresponds to have lower pitches. This happens also for light. Light can be described as a wave. So it behaves more or less exactly like sound. If light is emitted by a galaxy, and this galaxy is approaching you like an ambulance, you are squeezing the wave of the light. Squeezing the wave of the light corresponds to higher pitches, which we know correspond to blue color. On the other hand, when a galaxy is going far from you, you are stretching out the wavelength of the wave of light, and lower pitches in terms of light correspond to red. So when we have an object, a galaxy approaching us, we can measure if it's blue shift, or if it is going farther from us, we can measure its red shift. And what Fritz Zwicky did was to start to measure the velocity of galaxies in clusters. Galaxies emit light. If they are moving, they can be moving far from us or toward us. And because we can analyze their light, we can compare the spectrum from these galaxies with the spectrum which we have now here to make fireworks, and we can estimate what is their velocity. And what Fritz Zwicky found is that galaxies in the coma cluster are moving too fast, too much fast. This is taken from his original paper, which was in written German. And here you can see dunkle Materie, I don't know if I spell it correctly, means dark matter in German. And what he found is that galaxies are moving too fast. And the only way to have them to move too fast is that you need not only gas in the cluster, but you also need to introduce an invisible matter, which is called dark matter. And you have to introduce it a lot. Here you see that he estimated that you need a density 400 times greater than what we derive from what we see. And this was in 1933, so 70 years before the bullet cluster. Not only, but we, in the 70s, between 1970 and 1978, this astronomer, Vera Rubin, she never got a Nobel Prize for her discovery, but she was very humble to say that she didn't discover anything. She simply found out what was already in the universe on plain sight and was just waiting for us to see it. She discovered evidence, a lot of evidence for the existence of dark matter. Why? Because she started to measure the rotational velocity of stars inside spiral galaxies. So, spiral galaxies like our Milky Way, the sun in this moment is moving together with the star which are around it around the center of the galaxy in a circle. Now, if we look to other galaxies, for example, Vera Rubin started from Andromeda, which is the closest, the companion of Milky Way. She started to measure the velocity with which the galaxies are rotating, the stars are rotating inside these spiral galaxies. Andromeda first, and then she started to observe more. Now, the point is, the rotation, the velocity can be obtained in exactly the same way as Zwicky said. So it's a combination of analyzing the spectrum, comparing with Doppler, see the redshift or blue shift. So here in this plot, we have the velocity on the vertical line and the distance from the center. Now, the point was that if the only matter in Andromeda and other spiral galaxies was only the matter which we see, so stars and gas, then the velocity of the galaxies should do something like this. You see, stars reaches a peak and then slowly decreases. Guess what? She started to observe Andromeda, she started to observe other spiral galaxies, and when she was measuring the velocity, she was finding this. It was raising, really, but didn't reach a maximum and was not falling down. So these points which you see here are real data points. And they're telling you that the velocity of galaxies and gas inside spiral galaxies does not follow the trend which should be if we only had visible matter. How can we explain this? We must introduce dark matter. This trend means that there is more matter than we see. Otherwise, these velocities, these galaxies, these stars would be so fast that they should be free. They should leave the Andromeda, for example. But if they are still tied to Andromeda, it's because there is some matter which is holding them. Now, again, do you think this is happening only for one galaxy? No. It's happening, whatever galaxy you see, here there is a very small collection of galaxies, spiral galaxies, you have always the same trend. In each galaxy which we observe, we need to introduce a certain amount of dark matter. So dark matter seems to be really, really important for the existence of the universe like it is. And this was not only because this picture has another interesting story. If you want, I remember for Fundasa, I gave like 2 or 3 years ago a talk where I was explaining it. What is this? Say it very simply. If we put some radio antenna and we check how it is the temperature in the outer space, we find it that it is the Earth is moving in a sort of cosmic soup. It's a very cold cosmic soup because it's only 2.7 Kelvin degrees, which is more or less minus 270 Celsius. But what is very interesting is that when you start to look to this soup, there are actually differences in temperature. They are very small. Here you can see 10 to minus 5. So they are really uh, not you would not be able to perceive this difference on say your skin because it's so small that you can only detect it with very sensitive satellites like Planck, which was a European mission. And now, independently of what it is and its origin, we have this in the sky. And we have found that this picture is very sensitive to how much mass we have in the universe. And there is even a simulator here from Planck. Here on the top right corner, you see our universe, how it looks. And then here you have a simulation. So now I will show you how it looks if we only had visible matter. You can see clearly from visual inspection that what we observe is very, very different from from what we should have if there was only normal matter, the matter which we are made of. Now, I will put some numbers which I know they are the numbers which we observe. These here we are saying that we have only 5% of normal matter and only 25% of dark matter in the total matter energy budget. And you can see that the picture of the simulation on the left part now is very, very similar to what we observed. It's not still totally the same because we are missing another object, another quantity, which will be described in another talk by Professor Capozziello in the next days for this project. But here we see clearly that if we want to have only a universe with normal matter, we are not able to describe what we see. So we need dark matter also at large scales. And it's also fundamental to describe what we call the large scale structure. In this picture, there is what is, I guess, nowadays, as for today, the largest collection of galaxies which we have made. There should be around 10 millions of galaxies. This is from a telescope which is called Dark Energy Spectroscopic Instrument. And you have to imagine that this galaxy, we only have 10 millions observed, but we have now a mission which is Euclid, and at the end of it, in next 5-10 years, we expect to arrive to billions of galaxies, which is a huge number, trust me. And these are real. This is the real distribution. And even here, even if it is plotted like in this way, bidimensional, you can see that there is more galaxies here. There is some void space here. This is called large-scale structure or cosmic web. And there is actually a simulation, which is called Illustris. And here I want to show you how much is important dark matter to understand simulation. Because in this video, you have on the left dark matter. On the right, you have gas temperature. So you see normal matter. And you can see that the more dark matter you put till some level, the more this web, this cosmic web, looks like what we see. And what is interesting here is that there are all these, which you see on the left, is invisible. So here we have a simulation in which these particles, they are mass particles, they behave under GR. And you can see that if you have dark matter, you should have a cosmic web, which unfortunately is invisible because it's dark. But on the corresponding of these, you should have clusters, galaxies, you should have filaments, and they should be more or less visible. And from what we know, from what we see, we need this cosmic web of dark matter. Without it, the universe would not look like it is. So you understand now that dark matter is everywhere. And now the point, the crucial point, what is dark matter? I'm going to give you the most sincere answer that you can get from me and from other colleagues. We don't know. We don't know, but not because we don't have any idea. On the other hand, we have too many ideas. We have so many ideas that here is a very short summarizing picture of all the ways in which we try to explain dark matter. But the point is that till today, none of these has been confirmed. So I can dare any of my colleagues to tell me that you may have some weak evidence in favor of some of them, but weak evidence does not mean that this is the solution. We don't have a solution as for today about what is dark matter. I will not talk about this, which is in white, because it's or gray, because it's more theoretical, and I guess that Professor Capozziello will talk about it because it also refers to dark energy. But this is theory, and as you can see here, there is a modified gravity. What does it mean? Well, in the same way, general relativity was an extension of Newton gravity theory, because Newton gravity was working perfectly here, but not outside, had some problems. And general relativity solved these problems. Nowadays, there are more and more people working in the scientific community who start to say the following. We need dark matter when we try to explain everything, use GR. We know that GR is very successful, but now the point is the following. What if the need for this component, which we don't know what it is due to the fact that GR is not the ultimate theory of gravity? So probably there is another extended theory of gravity which does not cancel GR, but extends it. Maybe if you, in this extended theory of gravity, you might explain what you see in galaxies in the bullet cluster without dark matter. So I guess I'm probably running out of time, but there are only a few slides left. So let us look what are the most credible, no, not more, some of them at least. So here on the orange, we have what they're called machos. Machos is an acronym for massive compact hollow objects. And I call machos because it's very funny, because in Spanish, machos means when you have a man, very virile man and so on. So it was a sort of joke. What are? Well, we know that we have a lot of planets. We have a lot of black holes. We have a lot of other objects which have such a low luminosity that we cannot see them. But they are there. So they play interaction through gravity, even if we don't see them. We have, I will not go into details of this, but we have made an estimation, and unfortunately, our estimations say that if we are very optimistic, we can describe 20% of dark matter with these objects. But this is a very optimistic case. More likely, we are on the lower side. So with this object, we can explain it from between 1% and 5% of dark matter. So still, we have a lot of mass which is dark. Other ways in which we can find candidates, all these blue, green, and others, are particles which we don't observe normally, but they could exist. So probably you know, in the matter which we are made of, the energy which we know, follows four fundamental forces. One is gravity, which is the weakest. You cannot screen it, but it's the weakest. Then you have electromagnetic force. Electromagnetic force is the force which is between charges. Then you have the strong nuclear force, is the force which holds protons and neutrons together to form nuclei. And it is the force which releases its energy when there is fusion, nuclear fusion, for example. And then we have a force which is called weak nuclear force. Is a force which is, among these, is weaker than electromagnetic and of strong, but not as weak as gravity. But it's called weak, and it appears when, for example, you have fission, when you have radioactive elements. They release energy, and this energy is released through this weak nuclear force. And here you have what is called the standard model of elementary particles. Here you have all the particles which we know. So you can see there is the electron. You don't find proton and neutron because proton and neutron are not elementary. You can divide them in smaller particles, which are the quarks, and they are made of up and down quarks. Here you have the photon, which probably you heard, because are the particles with which we can describe light. And then there is all these other particles, which are leptons, quark, other quarks, and so on. Here you also have antimatter. What is antimatter? For example, positron is a particle which has the same mass of the electron, the same other properties like spin, but has opposite charge. So now, going beyond the standard model, we have proposed the existence of other particles, supersymmetric, for example, particle, which are particles which have, for example, the same mass, the same charge, but different spin. So, for example, there is a supersymmetric twin of the electron, which has the same mass, the same charge, but has spin 0, for example. Or they have, if they have spin 1, they have spin 1/2, and so on. These particles are called weakly interacting particles, and they have been proposed to solve the problem of dark matter, because if they are massive and they are only weakly interacting, it means that they don't interact with us, and the chance to interact with it is very low. But they have mass, so they interact through gravity. And we have many ways to check for them. One of them is the Gran Sasso laboratories. They are in the center of Italy. This is the headquarters, but you have to imagine that the laboratories are below this mountain. So this mountain rises to almost 3,000 meters, but these laboratories are covered by 1.5 kilometers of rocks. And this is very good because downstairs we say that there is a sort of cosmic silence. So all the particles which arrive from the space are blocked. And only the particles which interact weakly have a chance to arrive there. And you have a lot of experiments. One of the most famous and recent is xenon. So you have to imagine that below this 1.5 kilometers, have a tank filled with xenon liquid. And when they have it, they leave the xenon there, with hoping to have the chance that one of these weakly interacting massive particles interact with the atoms which are here. What happens is that if they interact, they produce a flash of light, which is collected, and then they also produce other particles like electrons, which are also collected. So depending on how many flashes of light and how many particles we collect, we can estimate the mass and the existence of these particles. We also have another place where we can find for these particles, which is the Large Hadron Collider. This is a circle, this is below the ground, is long 27 kilometers between France and Switzerland. And here, basically, what we do is that inside this underground ring, we send protons and other hadrons, types of hadrons, in circle. But we have two circles, one clockwise and one counterclockwise. So then what we do is to accelerate them. We make them to go faster and faster. And then at some point, in these two tubes, initially they are moving separately, but then at some point we connect them. So what happens is that if you have protons very fast coming from here, a proton going very fast from here, they collide and they produce a lot of particles. This is the data recorded in 2010. So all these lines which you see are particles, photons and everything, which came from the collision of these protons. Now, what is the point of Gran Sasso laboratories, the Large Hadron Collider? What we are doing is to push the energy barrier. We are going to push the sensitivity of this instrument to detect these weakly interacting particles. What is the result? Here is a very technical plot, but I will summarize. So here on the horizontal, you have the mass, the hypothetical mass of these weakly interacting particles. And here you have, it's called cross-section, but it's a sort of probability of interaction. And what these lines are all the experiments which we have run. Whatever is above this line is discarded. And initially, WIMPs were supposed to be as good candidates for dark matter if they had stayed here, more or less. And as you can see, all the experiments which we are running discard this. So what we have is that the WIMPs particles should have lower and lower masses. But this becomes more complicated because if we have lower and lower masses, then we might not have enough mass to describe dark matter. And at the end, the picture is that from the lowest particles which we are hypothesizing for dark matter to the highest, which are around 1 solar mass, we have a range of mass which is 90 orders of magnitude. So we can go from 10 to minus 21 electron volts mass to 1 solar mass, which is a lot of kilograms. This is just to tell you how, I don't want to say how lost we are, but because everything of this is research, but how few things we know, despite all such evidence which we have about dark matter, we know very few things about it. And now this is the conclusion. I have only 2 slides left, which I call the philosophy corner. If I run out of time, maybe I can leave this for when we have the discussion.
No, it's okay. It's okay. Please
okay. So this is what is the attitude which we should have toward the idea of dark matter. And here we have this comic, no? So there is this penguin say, I'm a simple penguin. What's dark matter? And then the other guy who is observing says, it's a logic-based theory cleansed of the primordial mold of religious superstition. But wait a moment, because now he says, we can see dark matter. We cannot touch it. We cannot smell it. We cannot feel it. We cannot sense it. But it explains the universe. It's there. It's everywhere. And you see, this is, he has said, glorious. I got ice chills. This is just to let you understand that what is the attitude toward that the idea of dark matter is not easy, because here we have something which we know it should exist, but so far we have no proofs that it of what should be. So how, as a scientist, we are looking and we are searching. If there will be a solution, we don't know. Maybe I hope that it will be after I retire, so that I still have time to work. And then the last one, because this there will be for sure a way to discuss about it in the dark energy session and also in the discussion. Because I said that we need, in the universe, we know nowadays, that we need 5 times more dark matter than normal matter. So one could say, are we special? Because we are made of something which is actually not rare in the universe, but it is not that it's very far from being the majority of the mass. And maybe these can be discussed also in the last discussion session. So thank you very much for listening.
Thank you very much, Vincenzo, for this very exciting and very interesting and also provocative lecture. I think everybody will find it very, very, I would say, nice and provocative, as I said, and inspiring to think. I
Just in case you are wondering, this is a real serious television which has been called Dark Matter. And of course, I wanted to watch it, and it's really bad. But still, I wanted to put it just to tell you that dark matter is really everywhere, even in TV movies.
Right. The name which I remember when I was a student was not dark matter, but it was dark mass rather than dark matter.
Also.
In Polish, it means slightly, I would obscure dark mass. Dark matter sounds much better. But anyway, it is important that the problem exists, and the problem should inspire people to think of. And this is our main motivation to actually put the topic into our discussion fora. And I cannot see any questions, neither on the okay, I can see. Can be an effect predicted in which we can observe any interaction of gravitational waves with dark matter.
Well, yes, we can. I can tell you that I was working with my PhD student who is not here anymore in Szczecin, and we were working on using gravitational lensing of gravitational waves to infer information about the distribution of mass inside the lens. So yes, dark matter creates this curvature, and this curvature has influences also on gravitational waves. And actually, because gravitational waves are waves like light, they can be lensed. But of course, you don't see real images. You see a distortion in the gravitational wave pattern. So yes, we also studied it. So you can have it.
Thank you very much for answering. Okay, I would like to remind you that you are the guests of the Jerzy Stelmach Eureka Foundation, which deals with the scientific problems and transmits the scientific problems to the society. We are helped financially with the Polish Ministry of Higher Education and Science. And I would like to invite you for the next series, next lectures of this session, Dark Universe, Problems of Contemporary Cosmology. There will be another lecture in 2 hours today, Saturday the 8th, given by Professor Salvatore Capozziello from University of Napoli, and then 2 other lectures on Monday. Please visit our YouTube channel, www.youtube.com and then /Fundacja Eureka. Thank you very much for attending this special lecture, this main lecture of this session given by Professor Salzano. Thank you, Professor Salzano, for
Thank you for
giving
the
us, and
invitation.
thank you everybody for attendance, both on Zoom platform and on YouTube. And I invite you for the next events of this session. Thank you very much. See you soon.
Bye. Bye.